All right, Chem 1110 students, we are working on talking about molecules and how molecules act so that we can understand reactions. And here we're going to talk about the forces between molecules and then how they bond to form a molecule. The first thing we're going to look at is the effect of molecular geometry and polarity on whether a molecule ends up being polar or not. Pretty simple when you only have a diatomic molecule because you just use electronegativities. Remember, we can show dipole as an arrow, or we can use our partial charges with our delta symbol. Okay, if you have a molecule that's made up of 3 or more atoms, then we have to look at not only the polarity of the bonds, but also the geometry of the molecule. An example here is carbon dioxide. It is linear. The oxygen is much more electronegative than the carbon, but we see we have 2 oxygens, so they are pulling the electrons in equal and opposite directions. And so as a result, the bonds are polar, but the molecule is not. So here's another example, water. In this case, because the molecular geometry is bent, even though the strength of the dipole is equal on both sides, they are not opposite, and therefore water has polar bonds and it's a polar molecule. Another example is boron trifluoride. The fluoride is much more electronegative and it's pulling the electrons away from the boron. It says a symmetrical shape. This is a trigonal planar molecule, and even though they're not pulling directly opposite from one another, the effect is that the charge is equalized, and therefore the bonds are polar, but the molecule is not. Okay, so we are going to look at carbon tetrachloride, and then what happens if you replace one chlorine with a hydrogen. So carbon tetrachloride is tetrahedral, once again a 3-dimensional shape where everything is pulled symmetrically in different directions, and therefore they do cancel one another out, so the bonds are polar, but the molecule is not. But if you replace one chlorine with a hydrogen such that the various poles of electrons towards the chlorine don't cancel one another out, plus you have a dipole towards the carbon from the hydrogen, then this becomes a polar molecule. Another example of how you do this is to look at PCl5. You have to draw the Lewis structure and use the Vesper model to determine the geometry, and then you can see if the individual bond dipoles cancel, making it a polar molecule or not. So when we do this, we get this structure for PCl5. You can see it's a trigonal bipyramidal. And so we have 2 things to consider, the chlorines on the top and the bottom, which obviously are pulling equally and opposite from one another. And then you have that trigonal planar in the middle, once again a symmetrical triangle, and so those do cancel one another and you end up with a non-polar molecule. However, if we look at something like formaldehyde, which has a double bond, then we kind of go through the same exercise to see if this is a polar molecule. So first we draw the Lewis structure and we see that the carbon is double bonded to the oxygen, plus the oxygen has a couple of lone pairs. So there's a lot of electron density on that side of the molecule. And then you're adding the fact that the carbon is more electronegative than the hydrogen, pulling the electrons towards itself. Then we find that they do not cancel one another out, and so as a result you have polar bonds and the molecule is polar. Okay, now we're going to talk about intermolecular forces, and these are the things that cause the molecules of a particular type to actually interact with each other. They're attractive forces between neighboring molecules. There are 4 kinds of these intermolecular forces that we will discuss. Collectively, they're known as van der Waals forces. One of the things to be aware, there are some pretty good intermolecular forces at work in a solid or in a liquid where the molecules are very close together. But when you're looking at a gas, they're so far apart and they're moving pretty quickly, there are no apparent intermolecular forces. Okay, so the first intermolecular force is a dipole-dipole interaction, and in this case you have attraction between polar molecules because one side is slightly positive, one side is slightly negative. And so I have a little cartoon here of some liquid molecules. Remember, the blue side would be partially positive because it's lacking electrons. The red is the high electron density, so it's got a partial positive, a partial negative charge, and so you see the red and the blue line up. It's a little haphazard, but they line up. Whereas if we look at the solid, we get a nice organized arrangement so that the red and the blue are attracted and lay side by side because the positives and negatives attract one another. The magnitude of those attractive forces depends on how strong your dipole is, and here's just a reminder of what the red and the blue stand for. All right, so dipole-dipole interactions were actually discovered because of their effect on boiling point. And so you have 5 molecules here that have very similar molecular masses. So you would think it'd take the same amount of energy for them to escape from the liquid phase into the vapor phase, thus boiling. But we see that propane, which has no dipole-dipole interactions, has a very low boiling point of minus 42 degrees C, whereas acetonitrile, which has a dipole with that carbon nitrogen compound, just gives you a strong dipole of 2.9, and so the boiling point is 82 degrees C. All right, another intermolecular force that we need to consider is hydrogen bonding. It's a kind of a dipole-dipole interaction, and it has to do with molecules where a hydrogen is bonded to a small, very electronegative atom, such as nitrogen, oxygen, or fluorine. And here's just a little, cartoon of the positives and negatives lining up, and the dotted line is referring to that attraction to, say, other molecules in the gas or the solid phase. This affects boiling point pretty extremely. If you look, the x-axis is period and the y-axis is boiling point. So if we look at the second period or the second row of the periodic table, we're going carbon, nitrogen, fluorine, and oxygen, which is, of course, makes water. Very, very strong dipole interactions and hydrogen bonding, because the dipole is a hydrogen bond, which makes those boiling points very high. And we see, if we just look down group 4A, so carbon, silicon, germanium, tin, is almost a straight line, but the very extreme hydrogen bonding that you have in water, HF, or ammonia makes those sort of inordinately high. All right, a third form of intermolecular force are the dispersion forces. These used to be called London dispersion forces, and you may see that in some books. This is where you get an instantaneous dipole in nonpolar molecules, And the reason for that is molecules all have electrons on the outside. So when two molecules get close together, those electrons that are on the outside repel one another, and some of the electrons scooch over to the other side of the molecule, thus having an instantaneous or short-lived dipole. And there's a little diagram here that tries to show the effect of the dispersion forces. So we're going to actually try and apply this with these examples: carbon tet, acetic acid, an ether, and then hydrogen sulfide. Here are the structures. So we can see that in A, it's non-polar. Carbon tet, we talked about this before, so you only get intermolecular forces that are dispersion forces, which are the weakest. If you look at this acetic acid, it is polar. It contains an OH bond, and so it has dipole-dipole across that polar CO bond. It has hydrogen bonding because you've got the oxygen bonded to a hydrogen, and you have dispersion forces. When you look at that ketone, this is acetone, you have a polar bond, that's CO, but you don't have any hydrogen bonding, and so you get dipole-dipole interactions. And of course, dispersion forces. Everything has dispersion forces. And in the hydrogen disulfide, it is polar. It has no hydrogen bonding, so it has dipole-dipole and dispersion forces. All right, the last one is ion dipole, and so ions have a positive charge or a negative charge, and therefore they are going to be attracted to polar molecules. And an example is sodium chloride, which is an ionic compound. Sodium is positive, chlorine is negative, and it dissolves in water quite well because of this interaction. All right, now we're going to start talking about how bonds form. And the very first one we're going to look at are the valence bond theory. And this says that valence electrons overlap, and that's how atoms share their electrons. And so we just need for two orbitals to overlap, and the electrons then have to have opposite spins or be spin paired. And so what happens is this bond allows a lower potential energy for the system. And the example we use is a hydrogen-hydrogen bond forming H2 gas. And so you only have one electron in a 1s orbital, and those can overlap, as this little diagram shows. In two fluorines, you could get the same kind of overlap, except for the single electrons are in a 2p orbital, so they would have to overlap with their p's end to end. And this is, the orbital diagram for a fluorine, and that's where you have your single electron. And so in HF, you would have a 1s overlapping with that single electron in a 2p. So you have this diagram, and you can see the bond length and the bond energies that would be associated with that. So the bond length for HF is, you get a much tighter bond, and therefore it's a shorter bond, higher energy. And this is just that diagram of the energies, and you see as they get closer together and the orbitals actually overlap, you have the lowest potential energy, and therefore the most stable molecule. Now, that is the end of this part, because we're going to move on to a theory that explains more molecules after this.